Good morning, everyone. My name is Samira Chebbout, and I am a teacher researcher at Malek University in Algeria. Today, I will present our work on a data-driven framework for soil fertility prediction and nutrient recommendations. In this presentation, I will first briefly introduce the context and the problem we are addressing, then outline our approach and main results, and finally discuss some implications and perspectives. Agriculture must address a major challenge, the progressive degradation of soils. Soil fertility is a key factor because it directly affects crop productivity and quality. A rigorous assessment of fertility is therefore essential, both for an agronomic purpose, to anticipate deficiencies that cause yield declines and soil degradation, and for an economic purpose, to avoid wasting costly inputs and to preserve farm stability. Traditionally, soil fertility is assessed through soil sampling, laboratory analysis, and interpretation by an agronomic expert in connection with the farmer's field experience. This approach is reliable, but it has several limitations. It's costly, time-consuming, and not always accessible, particularly in certain contexts or for small farms. All of these reduces farmers' autonomy in decision related to fertilization and soil management. With the emergence of digital technologies and machine learning methods, new approaches have been proposed to assess soil fertility. Several recent studies have developed models that predict the fertility of agricultural soils from their physical chemical properties. This study highlights the potential of AI to better exploit soil data, but they generally rely on already annotated datasets and focus mainly on the prediction stage. In our work, we adopt a data-driven end-to-end approach. First, we construct an original dataset. Starting from laboratory soil fertility reports, we build a dataset where we manually enter the physico-chemical parameters for each agricultural soil sample. Second, we apply automatic data-driven annotation. We use clustering to group similar soils, and we define a fertility index that both validates the coherence of these clusters and allows us to assign fertility levels to each sample. Third, we design an end-to-end system using the annotated dataset. We train a fertility prediction model and derive agronomic recommendations, so we move from raw lab data to concrete guidance for farmers. Building on this observation, our study is structured around three research questions. First, how can we group soils into agronomically coherent classes based on their physico-chemical properties? Second, how can we build a data-driven fertility index to validate these classes and annotate the samples? And finally, to what extent can a system combining fertility prediction and tailored agronomic recommendations support farmers? This work will focus on agricultural soils from the east of Algeria. The dataset contained 129 soil samples, all coming from laboratory soil fertility reports. For each sample, we have a set of physical-chemical parameters, including pH, electrical conductivity, organic matter, available phosphorus, and both total and active calcium carbonates. Our workflow is organized in several steps. First, we apply clustering to the soil data in order to group observations into soil classes with similar profiles. We use the hierarchical density-based spatial clustering of applications with NOES algorithm chosen for its ability to detect clusters with arbitrary shapes, its robustness to noise, the fact that it doesn't require specifying the number of clusters a priori. We build a data-driven fertility index derived from soil data and trained models. A random forest model is trained to estimate feature importance, used as weights in the fertility score. The fertility index is used to validate cluster coherence. Clusters should show consistent fertility levels, annotate observations into fertility classes low, medium, and high. Box plots of the fertility index by cluster show a clear ordering. Cluster 2 has the lowest fertility index. Cluster 0 is intermediate, and Cluster 1 has the highest fertility index. This ordering is consistent with an agronomic fertility square, confirming that the clusters are meaningful. The annotated dataset contains 128 soil samples grouped into 3 fertility classes. The medium fertility class is the largest, with 72 samples, while low and high fertility classes contain 28 and 29 samples respectively. The classes are not perfectly balanced, but each fertility level is represented by enough samples to support further analysis and model developments. To prevent the model from focusing mainly on the majority class, we apply smooth, synthetic minority oversampling technique to the minority classes. Smooth does not simply duplicate existing symbols. It generates new synthetic examples for the minority class by interpolating between the k nearest neighbors in the feature space. Here, k is set to 5. Based on the annotated data, we train 2 models to predict soil fertility. No sign of overfitting. Training and validation curves remain close, and the gap is limited across all sample size. Both models generalize correctly on the validation sets. Both models achieve good performance and shown by their confusion matrices, but the random forest model clearly performs best overall. Agronomic recommendations are generated by applying deterministic rules derived from agronomic standards and optimal parameter values, which makes this component closer to a simple expert system than to a fully autonomous AI. Here you can see the web interface of the proposed system. The user inputs the soil parameters, the soil predicts the fertility level, and corresponding agronomic recommendations are displayed. This interface is intended to help farmers quickly interpret soil analysis and obtain practical advice. To sum up, we developed an agronomic decision support system for interpreting soil analysis results. The system combines 2 main modules: a soil fertility prediction module based on machine learning, and an agronomic recommendation module based on standards and optimal ranges of soil parameters. It's not a fully autonomous AI system, but rather a hybrid tool, AI for prediction combined with expert rule-based recommendations. As a future perspectives, we can enriching the data used by integrating additional parameters to refine fertility assessment and recommendations. Moving towards more intelligent recommendations, use user feedback and field results to adjust the rules and learn from real-world performance. Large-scale validation by testing the system across different phytoclimatic contexts and crop types to assess its robustness and identify its limits of use. Thank you for listening. I'm open to your questions.